In this lecture, I will discuss about the decoders. In the previous lecture, I discussed about the encoders. So this decoder performs the operation just opposite of the encoder. So in the encoder, we have seen, so it converts the so many number of input data lines. So that was 2 power n input data lines. It will be converted into only simple n binary code. So 1 to n is the outputs. So only n outputs, 2 power n inputs. So this is a encoder. So what is the advantage or application of this encoder? We have seen. So to store the information, more information in a given space, or to errorless, or to detect easily the error. Now whenever we are transmitting so much of data, so we will encode the different information into simple codes, then we will transmit. Now once we transmitted, so when we are receiving at the receiver side, suppose just an example, so we received this code, so we can say simple a binary code. So a binary code is received. Now we have to extract the information from this code. So that is our aim. So what we do is we will give it to a decoder, right? So what is the decoder will do? It will take this binary code. So that is n-bit binary code. So I will take it as n-bit binary code. So it will be reproduced our 2 power n data lines. So what is the information, original information? It will be converted into the original information. So that is the process. So encoder will perform, it will take so many data lines as an input, and it will convert it into simple n-bit code, binary code. Then at the receiver side, so again we have to get back our information. So that's why we will use this decoder, so to get back the correct data. So this is n-bit data, and we'll get a 2 power n data lines, right? So that is some introduction. Now we'll see the definition. A decoder is a combinational circuit that converts binary information from n input lines, right? That is n input line we receive from the receiver to a maximum of 2 power n unique output lines, right? So what are they, how to convert from n-bit to 2 power n, that we need to see. So it is the 2 power n unique output lines. So that we have to remember, n input data lines, and or we can say n input binary code and 2 power n unique output lines, right? So that is this decoder introduction. So the decoder will contain the n inputs, right? N input or n binary code. So the decoder will contain n inputs and 2 power n outputs, right? So generally we say this is if I say this is m is equal to 2 power n, this is n to m line decoder. So the other name we can say, or we can say n by 2 power n decoder, right? So what is the size of this decoder? I can write as n by 2 power n, that is n input line, 2 power n output lines. So this is the decoder. Now if n is equal to 2, so what is this? It will become 2 by 2 square. That means 2 by 4 decoder size, right? That means 2 input as a binary code, and it will convert it into 4 output lines. Similarly, if n is equal to 3, so it will become 2 by 3 means 3 by 8 decoder, 3 into 2 cube, so 3 by 8. N is equal to 4 means 4 by 16 decoder, etc. So these are the different sizes depending on this n, that is n input data lines. We'll see decoder with enable input. So that also we have. Now we'll see decoder with enable inputs. That is, so we are giving some extra input, so which will control the operation of this decoder or encoder also. We have seen for encoder also. That is, so this is like a active high enable input. So this is called active high enable input. That is, whenever the active this pin is 1, so it will enable the circuit. So that means it performs the operation, or it perform the conversion. So whenever enable is equal to 0, so it will disable the circuit. That means no conversion will take place. So that is about this one. So this is like a switch. Whenever switch is on, so it will perform the operation. Whenever switch is off, so no operation. So something like this. So always whenever we purchase some ICs, always you will see a enable pins. Sometimes we may have 1, sometimes we may be 2 or more than that also. So depending on this enable pin configuration only, it will perform. Even when we give some inputs, if we don't give this enable pin as high, it will not perform the conversion. So this is like active high. Sometimes we may have the opposite way, that is active low enable input. So whenever active low means the notation is a bubble will be there. So this is like opposite, that is whenever E is equal to 0, it operates, that is it enables the circuit. Whenever E is equal to 1, so it's disable the circuit, that means no operation, right? So when we design, so we have to consider this enable pin also. So that is, so the enable pin always will be there in logic diagram also. So that we have to discuss, right? So this is about the with enable pin, right? Now we will see how to design 2x4 decoder. So that is, it contains two inputs X and Y, four outputs capital Y0 to Y3. So we will have different variable names A and B, Y0, Y1, Y2, Y3, or so D0, D1, D2, D3, etc. So there is no we have to follow only particular variable names, right? So that is our wish. Now, how to perform, or what is the uniqueness we need to give here? So there should be some uniqueness to the outputs. So what is that uniqueness is, suppose wherever there is a two inputs, so what are the, how many combinations will be there? Four combinations, 0, 0 to 1, 1. Now what we do is, we will assign what is the decimal number, equivalent decimal number. This is 0, this is 1, this is 2, and this is 3. So what is this uniqueness is? So what is the decimal number? 0. So give the subscript 0 the high value, the remaining all give as 0. Though this is subscript is 0, so that is decimal is matching. Similarly 0, 1 means 1. So give the subscript y1 as 1, the remaining all 0. So there should be uniqueness we need to follow. So we should not make two zeros or two more ones, etc. So there should be some uniqueness. That uniqueness what we are providing is the corresponding decimal number with the corresponding y0, the subscript, we are making the function value as high. Similarly 1, 0 means 2. So 0, 0, 1, 0. The last one is the y3 will be high. So this is some uniqueness we are giving. Now once we form a truth table, so how many outputs are there? So 4 outputs. So we will get 4 Boolean functions, or we can say logic expressions. Now if I see the y0 function, the function value is 1 at only for one input combination. The other input combination is 0 only. So it is nothing but simply NOR function. If you observe, so x plus y whole bar. So 0 plus 0 whole bar is 1. 0 plus 1 whole bar is 0, and so on. So this is simply NOR function. So how can I write the function value y0? Simply I can write as simply y0 is equal to x plus y complement, or simply x bar y bar. What is this x bar y bar? It is nothing but 0, 0. So this is nothing but m0, right? This min term. So if I see this remaining functions, I can see only one value is set for all the input combinations. So I can write simply the corresponding min term. So for this one, I can write simply x bar into y. For this one, I can write x into y bar. The last one, I can write simply xy. So those are the logic expressions we will get. So y1 means, so I will get x bar y. y2 means I will get x y bar. y3 means, capital Y3 means simply xy. So these are the nothing but the min terms, right? m1, m2 and m3. So we get the min terms as the logic expression of this decoder output. So once we get these logic expressions or Boolean functions, so how can I draw the logic diagram? So depending on the gates. So if I see x bar into y bar, so what is this? If I give x and y here, so I need to give it to one NOT gate to make x bar y bar. So both should be given to one AND gate to generate the y0 output. Then second one is x bar y. So already x bar is there, so I can take it like this and this y. So this is what? X bar y, which is nothing but y1. So next one is y2, which is x y bar. So I can take this x here, and y bar is already we made. I can take like this. What is this? y2, x y bar. So what is the last one? X y. So this is x and this is y, right? So what is this? Simply y3. About the logic diagram of the 2x4 decoder. If you see, this y0 is simply representing simply what is this? X bar y bar, one min term. This one is simply x bar y, another min term. This one is x y bar, another min term. This is x y. So we are generating simple the min terms, right? Corresponding min terms of the inputs. So there is 0, 1, 2, 3 and so on. Right. So this is about the 2x4. Next we will see the same 2x4 decoder with enable input. Right. Now we will see how to design a 2x4 decoder with enable input. Right. So first case we will see active high enable input. In the second case we will see active low enable input. So in the truth table we have to include this enable pin also. Why? Because whenever this enable pin is high, the circuit should operate or should convert. If enable input is low, it should not convert or it should not do the operation. So that's why we need to add this in truth table or functional table. So whenever this enable input is 0, right? So whatever the combinations, so I have to include the don't care. So whatever the combination, it will not give any the corresponding output. So it will be all zeros, right? So for enable input is 0, don't care means whatever the combination. So 0, 0, 0, 1, 1, 0, 1, 1, it will simply give the all zeros. So that is no conversion is happening. The second case is the enable pin is 1 and the corresponding input is 0, 0, right? So what is the output? So what is the 0, 0 means the subscript 0. So this output value is 1, the remaining will be 0, 0. The second one is 0, 1. So that is, it should be 1 for all the 4 conditions. Then only it will convert. Next one is 0, 1. So 0, 1, 0, 0. Third case 0, 0, 1, 0. Fourth one 0, 0, 1. The corresponding subscript will be high. Right? Now if I write the logic expressions, so y naught will become now x bar y bar into e. Yes or no? Because see here, whenever this is 1, then only I will get as x bar into y bar equal to, right? Similarly, what is y1? X bar y into e. What is y2? X y bar into e. What is y3? X y into e. Now if I see, if e is equal to 0, the y naught will be simply 0. If e is equal to 1, then only I will get a x bar into y bar. So this is about the logic expression for this 2x4 encoder with enable input. Right. Next we will see for this one also. Then we will draw the logic diagram for both. So 2x4 same active low. So what is this active low means? Whenever enable pin is 1, so it will not do the any operation or it will be simply disabled. So for any input combination, the circuit will provide all zeros. So it is not converting anything. Now in next case, when the circuit, the enable input is 0 for active low, so it will do the conversion. So 0, 0 means, so 1, 0, 0, 0. Similarly second one, the third one, same the truth table will get. Only variation is the enable input. So whenever enable input is 0, we will get the conversion. Whenever enable input is 1, we will not get any conversion. Now if I write what is y naught here, so y naught is equal to x bar y bar, but here e bar, right? So because this is 0, so 0 how can I write? Simply e bar. Next y1 x bar y into e bar, y2 x y bar into e bar, next y3 x y into e bar. So these are the logic expression for this 2x4 encoder with active low enable input. Now once we know this, so we can easily draw the logic diagram. So first I am drawing for this case. So y naught is equal to, so what I do is I will make, this is some x and this complement, so x bar, this is y and this is y bar. So what is the first case? And there should be some e. So this is enable input. Now x bar into y bar into e. So first one x bar y bar into e. So this is the AND gate. So y naught. Now there should be some point we need to remember. So whenever enable input is high, right? So the AND gate is like enabling, right? So when the AND gate enables, whenever this enable input is high. In the second case, x bar y. So this is x bar, this is y, and this is enable. So this is y1. Here also, whenever enable input is high, the AND gate will enables the operation. Next, x, this is y. So next one is x y bar. So this is x and this is y bar and this is the enable input. So what is this? Y2. So last case x and y. So this is x and this is y, and this is enable input. So what is this? Y3, right? So this is the logic diagram of this 2x4 encoder with enable input. So what is this enable input? Active high enable input. So next we will draw for active low enable input. I have drawn x, y and e, x bar, y bar and e bar. So what is the logic expression of y naught? X bar, y bar into e bar. So this is x bar, y bar and e bar. So what is this? And function, and get again. So this is y naught. Next one is x bar y. So x bar and this is y but e bar. So this is also and function y1. Next one is xy bar. So this is x and this is y bar and this is e bar. So this is y2. So what is the last expression? X and y. So this is x, this is y and this is e bar. So what is this? Y3. So this is the logic diagram for the active low enable input 2x4 decoder, right? Next we will see the same. So I will go for 1. So we will take it as active low outputs. So if you have seen this truth table, so we are taking the 1 for representing. Now we will take the opposite case. Now we will see 2x4 decoder with active low outputs. So what is this active low outputs is? It is similar to the active low enable inputs. So what was that condition? Whenever enable input is equal to 0, so it is operating. Similarly, we will get the same conditions. That is, when we take this the truth table, so here the corresponding the subscript bit is getting high. So just opposite means corresponding it will become 0, the remaining will become high. So something like this. So what is this active low output means? So 0 0 means subscript is 0. So in this place the function value will become 0, the remaining positions it will become 1. So what is this meaning is, if I make the opposite, so 0 bar means 1 I will get, 1 bar means I will get 0 here. So that's why you are placing a bubble in front of this output terminals. So this is like a opposite of this active high outputs. Generally if there is no bubble, we can say active high inputs or active high outputs. So this is like other way we are designing. So 0 1 means again subscript is 1. So at this position the function value is 1, the remaining positions 1. Similarly 1 0, here 1 0, the remaining positions 1, here 1 1 1 0. Now how to write this function? So y naught is equal to, so what is this function? So here we need to write the max terms. So what is this? Simply x plus y. Next y1 is equal to, what is this? X plus y bar. Similarly what is y2? Y2 is this one, x bar plus y. Next y3, simply x bar plus y bar, just opposite of the previous case. So now we will get the some max terms, right? Now we'll see how to draw the logic diagram for this 2x4 decoder with active low outputs. Now we got the logic expressions like this, y naught is equal to x plus y and so on. Now if you see, if I substitute 0 plus 0, so what is the output? I will get y naught equal to 0. 0 plus 1, I will get 1 and so on. Similarly y1, 0 plus 0, see 0 plus bar, y bar, so I will get 1, 0, 1, 1 and so on. So even if you substitute these values, I will get these function values only. Now how to draw the logic diagram? So what is first one? X plus y. So this is here x and this is y, but x plus y means OR gate. This is y naught. Yes or no? Next one is x plus y bar. So x, this is y bar. So one OR gate, again y1. Next one is x bar plus y. So this is x bar and this is y. One more OR gate, this is y2. Last one is x bar and this is y bar, OR gate y3. Now this is the one way of implementing the 2x4 decoder with active low outputs. The other way is using only NAND gates also we can go. So that is, I have written like this. So this is x plus y. Y naught is equal to x plus y. What I do is, two complements I have made. Then, so first complement will be using the De Morgan's theorem. I have written like this, x bar y bar whole bar. So the second one is x plus y bar whole bar means it will become x bar y whole bar. And the second one and third one similarly, right? So how to draw this one? X bar y bar. So I have to take x bar and this is y bar, give it to one NAND gate, which will become Y naught. So if I see the decoder with active high output, so we got Y naught is equal to X bar Y bar, right? Now if I make one more, okay, what is this, one bubble here, then I will get the whole bar, so which will become with active low outputs. So that's why generally we see in gate exam or in that any textbook, you will see with active low output means always you will see the NAND gates. But it is not about the uniqueness, so we can go for this one also. This is also correct, right? So but we have to use the NOT gates and OR gates here. So here we can simply represent this what you call the complements also using NAND gates. So this is one way of drawing the logic diagram. So what is the next one? X bar Y whole bar. So X bar and this is Y, whole bar means one NAND gate. So this will become Y1. Next one is XY bar. So X, this is Y bar, one NAND gate, Y2. Last one is XY whole bar. So X and Y, this is whole bar, NAND gate, Y3. So this is the logic diagram for this 2x4 and decoder with active low outputs, remember, right? So depending on the situation, depending on the applications, we have to use this type of gates. So we may get questions from this active low enable input or active low outputs also. So we have to careful about this active low enable input and active low outputs also. So whenever there is an AND gates at the output side, so we can say this is a active low outputs. Then the truth table will be opposite of the just active high output. So we will get the opposite. See here, this is the corresponding truth table for active low outputs. But if I see this one, so this is looking like an active high outputs. So whenever there is no bubble, active high outputs. Whenever there is a bubble, active low outputs. Similarly, when there is no bubble, active high enable input. Whenever there is a bubble, active low enable input. Right. So this is about the 2x4, all possible combinations. Right. Now we'll discuss the 3x8 decoder. Now how to implement this 3x8 decoder is, so it contains 3 input binary data and it will convert into the 8-bit data, or we can say 8 data output lines. Now we'll discuss the 3x8 decoder. So it contains 3 input binary data, or we can say 3 input binary, and it will convert it into 8 data lines, output lines, or we can say 8 data bit also, right? So what is the operation? So very similar to this 2x4 decoder. So 3 input bit means we will get 8 combinations, or 000 to 111. Now for each bit combinations we will find the decimal number, so it will become 0, 1, 2, 3, 4, 5, 6 and 7. So for each subscript we will make it the function value is high. So 000 means the first function, that is Y naught, will be 1, the remaining all zeros, right? So filling truth table is dead easy. See the combination of the input, so corresponding the subscript, the function value subscript will be 1. So 0, 1, all zeros, right? Similarly 2, so 0, 0, 1 and so on. So what I do is, so 2 means he, so that is 2, 3 means here, 4 means here, the 5 means here, 6 means here, the 7 means the last one. So remaining all zeros, so that we can make like this. We have to fill the truth table like this. So the corresponding decimal number and subscript we have to see, and we have to place ones. So whenever we place opposite, so we have to place the bubbles in front of the output terminals. Now once we know the truth table, how to find the logic expression? If you see this function, that is Y naught, if you see this column, only for one input combination the function is high. That means the corresponding min term we can simply write as a logic expression, similar to the 2x4 decoder. So what is Y naught? Simply the min term. 0 means X bar, Y bar, Z bar. 1 means X bar, Y bar, Z. 2 means X bar, Y, Z bar. 3 means X bar, Y, Z. There is no difficulty when we write the logic expression for this decoder. So it's very simple. Even without seeing the truth table, we can simply write. So see the subscript corresponding the binary number. So that is 4 means 100. So that is X, Y bar, Z bar. 5 means 101. So that is x, y bar, z. 6 means 110. So x, y, z bar. 7 means 111. So simply x, y, z. That's it. So in decoder, we will get output functions as all the corresponding the min terms. There is no the other option. So we will not get x plus y into z or something. So we'll get directly the min terms in decoder. So how is the logic diagram? The first one I am taking directly, that is x bar, y bar, z bar, AND gate. This is y naught. Next one is x bar, y bar, z. So x bar, y bar, z, AND gate. So you can write as we have designed for this 2 by 4. So x and complement, y and complement, z and complement. So this is also one way we can simply write down the logic diagram. That is x bar, y, z bar. 1 AND gate. This is y2. Next y3. So x bar, y, z. 1 AND gate. So I will get y3. Similarly y4 to y7. So similarly I have written for this y4, y5, y6 and y7 the logic diagram. Now if we include the enable input, so what is the extra we will get is 4 input AND gate. So extra and the enable pin will come. That's for each AND gate. If it is active low, so we will get the E bar as an input. Right? Very simple that one. So no need to again draw the same logic diagram once again. Right? So this is about the 3 by 8. Similarly, we can go for 4 by 16 decoder also, but that is not necessary. So very simple. So we can draw easily truth table and logic diagrams. But in the exam, what type of questions we will get is, we will not get questions like this. So now draw the truth table of this 3 by 8 decoder, etc. So we'll get questions like this: using 2 by 4 decoder, implement 4 by 16 decoder, or implement 3 by 8 decoder using 2 by 4 decoder, or implement 4 by 16 decoder using 3 by 8 decoder. So implementing the larger decoder sizes using the smaller one. So that is the important. So that we'll see in the next lecture.